Okay, so last time we were considering the so-called path independence of the line integrals, right? We see that in some situation, the line integral is dependent on the shape of the path you choose, but in some cases it doesn't. And well, and later we talk about the so-called conservative fields, right? So if we have a conservative field, then and when we do line integrals on it, and then we will have this path, this nice property of this path independence. And so and last time I also introduced the definition of conservative fields is that if you can write the vector field as the gradient of some potential function, then that is a conservative field, right? So and so the summary, right, is given in this slide, right? So and so now before we move on to the next item, so let's consider one vector field and see whether it is conservative, and if it is, how do we find the potential, the corresponding potential function for this field? Okay, so this is just the same example in this slide, but I'll just do it by handwriting here. Okay, so this is the vector field that I'm going to talk about. So again, it's in a two-dimensional space. Okay. So suppose I have this vector field here. Okay. So now if I want to test whether this is conservative, right? So what do we need to do? So last time we have introduced this test using derivative, right? So let me call the x component to the capital M, and this y component to the capital N, right? So what we need to test is whether this partial M, partial y would be equals to this partial N, partial x. So if you try to do the partial M, partial y, what you will find is x squared times 3y squared. Right? And on the other hand, you try to do partial N, partial x, then you will have y squared 3x squared. So these two are equal to each other. Right? So first step, so we show that this is a conservative field. Okay. So next, I want to ask the question that so now I know that this is a conservative field, so that means that this field must be able to written as the gradient of some scalar potential function, right? So now how do we find this v? Okay, how do we find this v? So because I know that this field is a gradient of this potential function, so that means the x component, right, the M, must be this partial v, partial x. So, and on the other hand, the y component of this field N must be written as partial v, partial y. Right. The question is, how do we figure out v? So if I take the first equation here, so partial v, partial x equals x squared times 1 plus y cubed. So if I integrate both sides, then what you would have is v equals, right? I'm doing this integrate with respect to x, and so I integrate both sides like this. So v equals to the integral of this, right, which is just x cubed divided by 3 times 1 plus y cubed. But that's not the end of the story, because if I add some more function behind, which only depends on y but not x, then if you take the partial derivative for this v with respect to x, you get back the same result. Okay. And also, of course, if I add some constant behind, right, and you take the partial derivative, it goes away. So that means from this first component here, you can conclude that the v can be given by this plus some unknown function in y plus some unknown constant. Okay. So now if I take this equation here, okay, if I go to take the partial derivative of v with respect to y, then what we have is this. Right. So now, if we look at this, and also look at the second component that we have. Right. So this expression here at the end must be the same as this one. Okay, so then the goal is to find out what kind of f do we need in order to make this one to be equal to this one. Okay. So then I'm just go ahead to write down the equation. So the requirement is that y squared times 1 plus x cubed has to be equals to this. So after we arrange term, you'll see that f prime y is just y squared. And again, if you integrate both sides, okay, then you'll find that f of y is y cubed divided by 3 plus, again, some other constant. Let me call this c prime here. So now I figure out this f of y, okay, and then I can go back to the original expression here. So right, so then at the end, this v as a function of x and y is given by plus some unknown constant c. Okay, but again, that one is I cannot figure it out unless you give me more information, right? So just like if you have the electric field and you give me the potential, right? But then you can add any arbitrary constant to the potential and still give me the same electric field, right? So that's why the C is something that we cannot figure out unless you give me more information. Okay. Yes. Can we not just integrate for dv by dx and add that is round u by round y? Why can you not just add the two summation of the integral and get the which you mean this one? Like when you integrate f, we get that function on there. Okay. Why can you not just add the integrals of f and a to get? Why is that not possible? You mean add this one and this one together? No, like individually take the integral and add the result to the function. Why can you not do that together to take the function? Right. So you mean I do the integral one time here and then you do another integral one time here. Yeah. Right. And then so you mean you want to integrate this with respect to y. Yeah. Right. So what would you get? You get the do the integral with respect to y here. So what you get is so let me So if I try to integrate the second equation, that's what you get, right? So with respect to y, so then I would get this. So but plus some unknown function of x, okay, also plus some constant here, okay. So and now you said you want to add this and what this together. Where is the unknown function y and x started? I don't know if we do anything, but where did the echo point come from? So well, sort of. Right. So you don't understand why the f comes from, right? So yeah. You just take this down here. So and then I go back to do partial v partial x. Okay, if I go back to do this, and then what you get from the first term is go back to x squared and this, right? Yeah. And then this one, what you get is this. And then the c is just 0, of course, right? So then you get this. You see this partial f, partial x. Well, it must be 0, right? Because f is just a function of y, right? So this is 0. So that means that I cannot rule out the possibility that I have some function of y here, right? And indeed, in this example, you can clearly see that at the end of the day, f of y is not 0. You find something. You find some function of y here. Okay, so from this example, so here again, I just lay out the general process that we have just done, right? We have just done it already. So let me just quickly repeat it. Okay, so I have some conservative vector field, this one. Okay, and because I know that this is conservative, so that means this n must be able to be expressed as this partial v partial x, and this n must be able to be written as this partial v partial y. So now, just like what we did, is that if I take this first component and then integrate both sides with respect to x, then I have this v to be equals to this integral plus some unknown function f of y plus some unknown function c. Okay. So now from here, if we now take the partial derivative with respect to y, we get to here. Okay, this equation 3. But remember, this equation 3, okay, has to be the same as equation 2 at the end, right? So then from here, we will find out equation for this f prime y. Okay. And then we get f prime y, we can get f of y. Then we get the vector field v. Sorry, the potential function v. Okay, so this slide is just the same as what I've just written down. Okay, so next, what we are going to consider is another kind of line integrals. Okay, so what we have done before, right, is that if I consider a line integral around a closed loop C, right? So, and this is my small step ER, right? So, what we are considering is this. Right? So, and suppose this is my f vector at this point here, and because of this f dot dr, right? So when we do this, that means we only care about the component of the f that is parallel to the dr. Right. So, or I call this the tangential component of f. Okay. So let me call this f, right, tangential component of f. So this is tangential. I call it tangential because it's tangential to my curve C, right? It's parallel to dr. Okay. So that means when you do this line integral, your f dot dr, right, is just basically the magnitude of your tangential component, right, times the length of the dr. Okay. So what we are going to consider next is the other component, which I'll call it the normal component. Okay. So this is a component that is perpendicular to my dr vector, and I call this normal because this component is also normal or perpendicular to my curve C. Right. So this is my normal component. So that means I want to find. So what we want to find next is that instead of this line integral, I'm going to have this. Okay. So for every small segment, right? So I take the product between this dr, the length of this dr, and the magnitude of this normal component. Okay. So how do I express this integral here? Okay, so now I'm going to construct a so-called normal vector. Okay, a normal vector which point this way. Okay. So again, I call this normal vector because it's normal to my curve, perpendicular to my curve. Okay. So that means if I take the dot product between this f vector and this normal vector n, then I can figure out the normal component for this f, right? So that means the line integral that I'm going to find can be written like this. Okay. Instead of taking the dot product between f and dr, what I'm going to do is to take the dot product between f and this n dr. Okay. So n, normal vector. So this is the kind of line integrals that we are going to consider. Okay. So remember when we talk about this first kind of line integral, so if f is a force field, right, we understand that it has the physical meaning of work done. Right, so that's what we had last time. But of course, this vector field does not have to be force field. It can be other field. But then this line integral won't have the physical meaning of work done anymore. But it's still a line integral that we can do. Okay, so what we're going to consider next. Okay, so here you can for sure this is not work done or anything related. And in fact, what I want you to think about as a physical example, okay, is a vector field that is not the force field, but instead is the velocity distribution of air in some region in the xy plane. Okay, so I give this vector field to you. Okay, describe the airflow velocity at different points in this xy plane. So suppose I have this wet, again, this wet path or this wet boundary, okay, enclosing some circular region. Okay. So what I want to find is the amount of air flowing out of this region per unit time. Okay. So to do that, what you need to do is to consider, first of all, consider a very small segment of this entire boundary. Right? Just look at this small segment and calculate, right, how much air is flowing out per unit time. Okay. So what I have here is that I consider this segment and then I just zoom in. Okay, this is the zoom in picture. Okay. So now this is the length of this small segment, which is just the magnitude of this, my dr vector. So now what I need to find, if I want to find the flow per unit time, okay, across this small segment, I need to find the dot product between this airflow velocity and this normal vector, okay, times the length of this small segment of the boundary. Okay, so this is the flow per unit time. Okay, F dot n hat dr. Okay. So, and at the end, you understand that after we take care of this part, we need to integrate over every small segment, right, of the entire curve. Okay, but let's just look at this one first. Okay. So how do we find the NDR? Okay. So n is a vector as I require that is perpendicular to my curve, right? So dr is in this direction. Okay. So I'm still going to do the line integral in the anti-clockwise direction. So you can see that I want to find the normal vector which is perpendicular to this dr. Okay. And to do that, we need the help of the z hat vector. So this is my xy plane along this screen. So then the z hat vector is a vector that is pointing out of the screen. Okay. Just imagine that. Although nothing is living in this region, right? So all the airflow is still confined in the xy plane. But now let's just consider that as a z vector, right? So pointing out of this screen here. So if you take the cross product between this dr and this z vector, so just use your right hand grid rule, right? So my dr is pointing up like this, right? So and then my z vector is pointing to you, right? So you use a right hand grid rule, then you'll find a vector that is pointing, right, exactly along the n hat direction. So this is the formula that's for us to find the n hat dr. Okay. And other than that, z hat does not have other purpose. Okay, it's so only for us to find the n hat dr. So you can try to do another segment. So let's say I try this one. So this is my dr for this part. But again, if I want to do the right hand, use my right hand grid rule, right? So dr cross z, right? So then you get a vector that is pointing in this direction. So for any segment in this curve, right, just do dr cross z, then you'll find your normal vector. Okay, but of course the magnitude of this cross product, right, is just dr. Okay. So then this is my flow per unit time. Okay, so and now if I want to find the flow, right, across the entire boundary, the flow per unit time across the entire boundary, and I call that flux. Okay, there's a name. Okay, you learn it in your when you learn about electric field Gauss law. You have this flux of electric field. Okay, so this flux across the entire loop. Okay, but I should mention that when you learn about electric field, you consider the flux through a surface, but not usually not through line. Okay, but we will talk about that later. So this flux across this entire loop, right, is this integral. Okay, and I just told you that this n dr can be written as this dr cross z. Okay. So now let's actually work out a formula that we can use to actually compute the integral. Okay. So the first two steps are just what I just include in the last slide, right? And then remember, okay, this dr can be written as this dx x hat plus dy y hat. Okay. So then you have this. You take the cross product with the z hat. Right. So the first term x cross z is this minus y hat, and then this y hat cross z hat is that x hat. Okay. So then you arrive at this expression here. Okay. So next, I think you could expect what we need to do is again the parameterization, right? Because for the x and y, right, I need to use the parameterization to describe, right, the x, y point, right, in terms of t. So then this is just the parameterization that I'm going to do. Okay. So the dx, right, becomes this dx dt dt, and this dy becomes this dy dt dt. Okay. So remember what we had in, just do a recap. So what we had for this one that we have learned. Okay. For this one, we have this. Okay, so the one in red is something that we have learned before. Okay, but now we are doing this, then the formula of course will be different. Okay, instead of this m go with this dx dt, I have this minus n go with this dx dt, and here we have n go with dy dt. Now I have this m goes with this dy dt. But you could see that the procedures will be very similar to do, right? So these two types of line integral. Okay. So here, let's try again a simple example. So this is the vector field you have seen multiple times, and this circular path is also you have seen multiple times. I want to find the flux across this red circular, right, boundary. Okay. If you just look at this picture before doing the calculation, you expect something positive, right? Because if you look at the arrows, right, so they are all pointing out like this, right? So then at the end, you expect there's some positive, some outflow from this boundary, some positive flux. Okay. So to do that, again, parameterization, don't need to repeat it again, the same parameterization that you have done last time. Okay. And this flux, right, so I just can be written as this integral in terms of t, right, just using this formula here. And then at the end, you find some positive number as you expected. Okay. So now I just switch the field to this form, to this, remember this circulating field, okay? And if you go to find the this flux integral, this time you find 0. So again, if you look at this picture, it's also very reasonable, right? Because all the fields are going tangential to the circle, right? So that's why this the air is never flowing inside of this to the circle or outside of the circle. So that's why in this case, I have 0. Okay. So again, there's two more examples here, but these 4 pictures are something that you have exactly seen before, right? But here, this is something we have done, and here, if I just reverse the direction, and of course I'll get a negative number because now I'm getting inflow instead of outflow. Okay. When I get inflow, then the flux is defined to be negative. Okay, because the normal vector that we have is pointing out of the boundary. Okay, then if you take the dot product, then you get negative number. Okay. And for this one and this one, of course, they both get 0 because both are circulating. It's just that one is clockwise, the other counterclockwise. Okay, but they all move tangential to a circle. So that's why no inflow or outflow. So next, again, we are going to consider a very, very small loop here. Okay, so I'm considering a loop again of length dx and width dy. Okay, and suppose the center of the loop, the coordinate of the center of this loop is given by this x, y. Okay. So, and I have this 4 blue arrows, okay, indicating the field, okay, at these 4 different points. Okay, these blue arrows refer to the field. Okay. So if I want to calculate the flux right across this infinitesimally small loop, then again I have 4 sides to take care of. Right, this side 1, side 2, side 3, and side 4. Okay. So if I want to consider side 1, right, so I just take so the normal vector I have, what is the normal vector I have? If I consider side 1, the normal vector I have is pointing down, right? So it is minus y. And if for side 2, then my normal vector will be x hat. Right, side 3, positive y hat. Side 4, minus x hat. Okay. So then if I consider the flux right across side 1, I need to take the dot product between this green vector and this blue vector and multiply by the length of this. Right? And the same thing for the other side. So then that's why you can see that my flux integral can be written as the sum of 4 terms. Okay. So side 1 over here, you can see that I have this minus y hat here, and then the field, right, the vector field at this point, this arrow, right, is written here. Right, similarly, for this side 2, my n vector, normal vector, is this x hat. So I have it here, and of course my length here is delta y is over here, and then my force field, not force, but my field, right, here is given by this term here. Okay. You notice that the field I take here and the field I take here are referring to different coordinates. Okay, so because for side 1 I'm taking the field at this point, side 2 I'm taking the field at this point, side 3 at this point, side 4 at this point. Okay, so these 4s are referring to the coordinates for these 4 points. Okay. So now So isn't it very similar to what we have done last time with this circulation density? Right, so very similar. So then here, the first line here is just repeating what I have in the previous slide. And then again, I'm doing the group terms, okay? Because at the end, we want to write things as some partial derivatives. Okay. So I'm writing the second term here and the fourth term here as this fraction. Okay. So I divide delta x and then multiply delta x. And then the second term here is from the first and the third term. Okay. And then here I divide delta y and then multiply delta y. So you can see that the whole thing has this common factor, delta x delta y. Again, looking at this fraction, right, and then taking the limit by delta x delta y tends to 0, right, then of course, this one is the partial derivative of m with respect to x. And the second one is the partial derivative of n with respect to y. Okay. So then again, this flux integral, okay, can be written as this two partial derivatives added together multiplied by the area of the loop. Okay, again, this dA, right, is just dx times dy. So, and this sum of these two partial derivatives, okay, is defined as this divergence of this f, or known as this flux density. Okay. So that means if I'm going to find the flux across a tiny infinitesimally small loop, then it can be written as, instead of a line integral, it can be written as the flux density times the area of the loop. Okay. So again, here I give you an example. So suppose I have this vector field. Okay, so here you can see that in this region, okay, the vectors are all diverging out from a particular point here. And then on the other hand, in this region, okay, the vectors are all converging to this point here. So now for every point on this xy plane, right, you can calculate this flux density. If you go ahead and calculate that, you'll find something like this. Okay. So you can find that if you are in a region nearby this, like there's like a source of the outflow, right? So you get positive divergence or positive flux density. If you are close to this point which try to suck all the vectors into it, then you get this negative divergence. So remember, positive. So outflow will give you positive flux, but inflow negative flux. Okay. So positive, negative. So now if you are somewhere like in between, right? So you could see that your flux density is close to 0. Why? Because if you consider a small loop here, right? So you get inflow from the left hand side, right? But then you get outflow to the right hand side. Right? So in and out pretty much the same. So you are exactly at this point here, at this line here, you get 0 flux density. So next, when you look at this diagram, you know what I'm trying to do, right? So it's similar to last time that I'm going to decompose a big loop into small loop and then into smaller loops, right? Into smaller and smaller loops. So what I'm going to consider is this, starting with this rectangular loop. Okay, this is a big one, not an infinitesimally small one. Okay, a loop C, okay, and then enclosed by some region A. So suppose I have some vector fields, it's not drawn, and I want to find the flux across this loop boundary C. I want to find the flux integral. So again, so what I'm doing here is that I decompose this big loop into small equals loop, equal plus smallest loop. Okay. So now, if I ask the flux across this loop C1 and the flux across the other loop C2, right? So if I add them together, what would happen? Okay. So it's really this very similar argument compared with last time when we do the circulation density, right? So if I want to find out the flux integral, right, for C1, right, I need to take care of four sides. Again, 1, 2, 3, 4. Right. So and then if I want to find out the flux, right, across the other loop C2, right, I need to take care of these four sides. 5, 6, 7, 8. Right. So however, when you do side 2, right, if you find there's some flux, and then when you do side 8, you also find some flux, you understand that the magnitude of the result that you get from side 2 must be the same as the magnitude that you get from side 8, but with an opposite sign, right? Because whatever outflow, right, from A1 has to enter A2, right? So that's why if I get some positive number from side 2, then I must get a negative some number but same magnitude from side 8. So, right, and even the opposite way is the same, right? So if you have some outflow from here to here, then you get positive number here but negative number here. But the magnitude of that number be equal. Okay. So that means the contribution from side 2 and side 8 to cancel. Okay. So all you need to take care of is 1, 5, 6, 7, 3, 4. By this 6 side, and that is exactly form the boundary of this bigger rectangular loop. Okay. So at the end, what you're going to do, right, exact same figures as the last time here, is that I'm going to break down this big loop, right, into many small loops, right? So the region, but the total region enclosed by all the small loops, right, is just equals to the region enclosed by this big loop C. Okay. So then my flux integral, right, across the entire boundary C is equals to the sum, right, of all the flux integrals for this all small loop here. Okay. And this one is something that we have found just now, right? So the flux across this small loop, right, is written as the flux density times the area of one small element here. So then my flux integral can be written as, again, the double integral. Okay. So this is known as the normal form of Green's theorem. Okay. So last time we have the tangential form of Green's theorem. So this is the normal form of Green's theorem. Okay. So the tangential form, right? So tangential form is this one. Right. So this is the line integral that we use. Right. right? This is tangential form, just like the last time when we talked about it, right? This one. Right, so tangential form, normal form. Okay. So just one thing to remind you is that when you try to read some books, okay, so sometimes you see that the left hand side, they just write it as this, okay, but it's the same thing, okay, but they just use a slightly different notation. And also this one, when you read books, so they may write it in this form here. Okay, but you understand this one is really just this one. Okay. Okay. So in fact, in you can see this one in this slide here. This one. Okay. Okay, so now let's take a break here. We'll come back at 12:30. Okay, come back at 12:30. Continue. Sure. It's a different way to write it. So they just don't write down the parameterization, but they just write it in this notation. It's really the same thing here. So I find it easier to understand if I write in this form. Okay. So that's why in the lecture notes I just write in this form. But that's what I'm saying. When you try to read some books, okay, they like to write it.
For some reason, I see that this just confused me.
Right. So but just need to understand that this one is exactly means this one. Yeah. Right. Exactly means this one.
Okay.
Okay, so let's continue. So what we are going to do next is to consider some generalizations of our previous content. So we are going to consider vector fields in 3 dimensions, okay, instead of 2 dimensions. So if I have a vector field, okay, in 3 dimensions, okay, I can always write it as 3 components like this, right? Some scalar function for each component. So x hat, y hat, and z hat. So the 3 components, I call them m, n, and p. Okay. So again, if you want to ask the same question about doing line integral, so doing the line integral f dot dr, okay, so what we need to do is to, again, parameterize the path, but this time my parameterization, right, will have to be written as x hat plus y hat plus z hat, right? So x as a function of t, y as a function of t, and z as a function of t. Okay. But other than adding one more component, right? So nothing has changed. Okay, so my line integral, okay, this integral f dot dr, okay, going from my starting point r to my ending point s, like can be still written as, after parameterization, is the integral with respect to t for this f dot dr dt. Okay. So all we are doing is add one more component. Okay. Calculation procedures the same. Okay. So it's just more difficult to do the parameterization. That's it. Okay. So then the line integral, right, can be written as this one, right, integral over t. So again, I want to ask about the problem of conservative fields and the path independent. Okay. So this time, if what I'm going to tell you is that if in the 3 dimensions, okay, if my field again can be written as the gradient of some potential function, okay, so then my line integrals again will be path independent. Okay. But again, you can see that, okay, the procedures, right? So of this proof is just exactly the same as what we had for the 2-dimensional case, except that I have the additional term partial v partial z hat, and this dz dt. Okay, typo here. Right, so these are the 2 additional terms that we have. Okay, but the trick is the same. Okay, so if we consider this dot products, so then we can write this entire integrand as this. Okay. And this one you can again recognize that this can be written as the total derivative of this dv dt. Again, just a chain rule. Okay, so last time we used this chain rule for 2 variables, x and y. So here we use chain rule for 1 more variable, okay, x, y, z. But at the end, it can be written as the integral of dv dt dt. And that means this is equals to the value of this v function as the point s, the ending point, okay, minus the value of this v function as the initial point r. Okay. So now, again, asking the same question is that how do we test whether a vector field in 3 dimensions is a conservative field or not? Again, we are not going to do infinitely many line integrals to test that, right? So again, we are going to use a derivative test. So if I have this vector field, right, so mx hat plus ny hat plus pz hat. So if it can be written as the gradient of some function, right? So that means the m can be written as partial v partial x. And then this n can be written as partial v partial y. And then this p can be written as partial v partial z. So again, the trick is to rely on the fact that the orders of taking derivatives doesn't matter, right? So because partial v, right, partial y, partial x has to be equals to partial v, partial x, partial y. So this is the properties that we'll rely on. But similarly, by taking derivative for y first or z first, to give you the same result. So because of all these three equations, okay, so then it gives this set of equations here. Okay. So these three are exactly equivalent to these three here.
Sorry, potential part. For example, we have we see any intermediate values between our potential to our potential well as sound as trivial, then what we do is
So for non-continuous, for sure we cannot use this method to test, right? So, but if you say that you still want to find the let's say find the field from the potential, I think you will be running into problem, right? So suppose you have a discontinuity in the potential, right? So at the boundary, then I believe you have at that exact boundary, right? So you have the this discontinuity for your field as well. So okay, so this one is only for continuous and differentiable potential function. Okay, so again, and this is just one thing that which I will say later, but here I can just mention it. Okay, so later when we talk about the vector fields in 3 dimensions, again we'll define the circulation density. Okay, and we'll use this symbol, okay, the curl of F. Okay, this is the circulation densities for this vector field in 3 dimensions. And in fact, this one I'll talk about more, but I just want to let you see the formula for a second. Okay. So when we learn about the circulation density for this 2-dimensional vector field, we only had this term here. Okay, you still remember this Green theorem for this tangential form. Okay, so for the 3-dimensional vector field, okay, to show that the circulation density is defined this way. Okay, and one thing you can see from here is that if this one is 0 and this one 0, if they are all 0, okay, so that's corresponding to all the components for the circulation density to be 0. Okay, and that will give you the conservative field in 3 dimensions. Okay, so again, I'll go to this curl of F in details later. Okay, again, just the summary, but this is essentially the same as what we had from the 2D field, right? But it's just that now the derivative test, we have 3 equations to take care of instead of 2. Okay. So this is the end of the first part 1 of the lecture notes of this chapter. Okay, so I'll move on to part 2. So in this part, we'll be all talking about vector fields in 3 dimensions. Okay. So again, we'll start with the concept of flux. Okay. So just now we talked about the flux across a boundary line. Okay. So what we are going to talk about next is the flux through a curved surface. Okay, a curved surface in 3 dimensions. Okay. So before we do that, okay, we need to learn how do we find surface areas and surface integrals. Okay, so this part will be related to chapter 2. Okay, again, we are going to do some kind of double integrals here, but we are not finding areas or volumes. So here we are finding the surface area of some function. Okay. So again, you can see that I have this function. Suppose I have this z equals f(x) and y. So suppose this is represented by this curved surface S. Okay. So I want to find the surface area, this F. Okay. And within some region, okay, okay, suppose I set this boundary here. You can see that I set this R. Okay. So what this R means is, suppose if I project this curved surface on this plane, okay, so then I get some region here, this R. Okay. So that means I want to find, okay, within this region R in the xy plane, okay, what is the total surface area, right, of S directly above this region R. Okay. So what do we do is that we are going to consider, okay, a small area element. Okay. So first of all, you can see that I have all this grid here. Okay, they are all curved lines now. They are not just rectangular grids. Okay. We could see, you could imagine that if I project this curved grid, okay, onto the xy plane, okay, then we get back a rectangular grid. Okay. So just like this. Okay, so here I have this rectangular grid. Okay, something like this. So I'm saying that if I project this curved grid on the xy plane, we'll get back to a rectangular grid. Okay. And also, okay, so for each element here will correspond to one element up there. Okay, so here I have all these little square. So up there I will have a little bit of this curved surface. Okay. So then if I just zoom into a particular element here. Okay, suppose I zoom in to this one here. I draw it here. Right. So here, if I do the projection, maybe I will hit this one here. Right. So then this little dA here, okay, is the projection of this little piece of my area element. Okay. So look at the projection. Okay, suppose the projection, right, the width, the length of this projection area is the length is dx, right, and then this width is dy. Okay, so this dA is just dx dy, right, the area. But what we care about is not this one. What we care about is what's up there. I care about the area of this element here, okay, so which we call it d sigma. Okay. So, and here I construct a normal vector n. Okay, so this normal vector n is perpendicular to this d sigma plane. Okay, so now I'm going to do projection, right? So this d sigma cosine theta will be equals to this dA. Okay, so cosine theta is the angle between this n vector and this dashed vertical line. So that means so dA, right? So dA is basically is you could imagine if there's sunshine from above, right? So this dA is the shadow, right, of this d sigma. Okay. So this d sigma cosine theta is this dA here. Okay. So d sigma is well, you could imagine it's slightly larger than this dA. Right. So now cosine theta, right, can be written as the dot product of this n hat and this vertical line, right? So n dot z, n hat dot z. So then now my d sigma can be written as dx dy divided by n hat dot z hat. Okay. So now what I need to do is to, right? So consider the appropriate boundary, right? So add up all the d sigma up here. Okay. So, well, I'll show you how to. Well, setting the limit shouldn't be a problem for you now because you, for example, if I just consider this rectangular region, right? So you understand that it's just some constant x boundary and some constant y boundary. So that one won't be too tricky. But first of all, we need to understand how to find this n hat dot z hat. So that's the key for finding this surface area. So what we are going to do is that I'm going to rewrite this as z equals fxy in a slightly different form. Okay, I call this gxyz to be equals to z minus fxy. So then my z equals fxy can be also expressed as g equals 0. Right. So then that comes back to the concept of contour lines. Okay, so remember if I have z equals fx, then I have this mountain, right? So then if I set fxy equals to some constant, then I have a particular contour line of my mountain. So here the idea is that I have this function, okay, g equals xyz. If I set this function to be a constant, so that means this can be treated as a contour surface of a free variable function. So this is a generalization. Right? Some curved surface, by setting that to some particular value, contour line. So now some free variable functions, and then set it to some constant, then I get a contour surface. Okay, not contour lines anymore. So now that means my z equals fxy can be treated as a contour surface of the g function. Okay. So now remember that when I take the gradient of a function, okay, so the gradient vector is always perpendicular to the contour surface. Okay. So that's exactly what we want. We want to find the normal vector, right? So normal vector is the vector that is perpendicular to the surface. Right. So then if we take the gradient of this G, then we will find out the vector that is normal to this surface. Okay. So, but however, when we take the gradient, okay, when we take the gradient, it is not, it may not be a unit vector, right? It can be a long vector, it can be a short vector, but we only want the direction. We only want the direction of the gradient of G because we only want a unit vector. But that's not difficult. We just take the gradient and then we divide it by the magnitude of itself. Then we'll find the normal vector n. So now let's work it out. So how do we find the gradient of G? Okay. So because if we can find the gradient of G, then we successfully find the expression for this small area element. Right? Then we can do the double integral. So remember, by definition, by what we define, G is equals to Z minus XY. So taking gradient, that means just take the gradient of this, right? And then just use the standard formula that you have before. Although the gradient, when we talk about gradient last time, we only have x hat and y hat, two components, right? But now we have three variables. You just keep adding the partial f partial z hat, right? And here the partial f partial z is just one, right? So that's why here I have this expression here. So now I want to find, right, the magnitude of gradient divided by the magnitude of gradient dot z. Okay. So then what is the magnitude of gradient? Magnitude of gradient is just the square root of this square plus this square plus this square. And also the z component of the gradient of G is simple, it's just one. Right. So this is just the numerator. The denominator is just one. So that's why this whole term is given by this. Okay. So that means d sigma. D sigma is this whole term here times dx dy. Okay. So then at the end, if you want to find the double integral, right, the surface area, then you just do a double integral for this. Okay. So of course, I'll give you examples. But before that, let me talk about another way to show that why this element is given like this. Okay, because you might not feel very comfortable to think about gradient and all that. Okay, some of you might not be comfortable thinking about this gradient and all that. So I want to give you an alternative way to show that why my d sigma is given by this without using the concept of gradient. Okay. So this picture over here is what I have shown you in the first slide, right? Just this one. So I draw it here again. And my purpose is to show you that this d sigma is given by this formula here. So look at the geometry here. So here, of course, this is the dx dy, right? This is the dA, and this is a tilted surface, right? And then, in fact, this is, if it is small enough, right? Basically, this is close to a parallelogram. Okay, so this green one. Okay. And if it is very close to a parallelogram, then I can use this formula to calculate its area. So what is this formula? This formula is U cross V. So U is a vector, this vector along one of the sides of this d sigma surface. And this v vector is this one, this blue vector, which goes along the other edge of this d sigma. Okay. So the area, right, the area of this d sigma, right, it's just given by u cross v, the magnitude of u cross v. This is, I believe, this is something you learned before, right? The area formula. The u cross v is equals to, right, so this parallelogram formed by these two vectors. So then the key is to find out u and v, right, to find out u and v. So now if I draw this plane out, so this is what I got here. Now if I draw this plane the other side, this is what we have here. Okay. So my job is to find out this v and this u. Then I can do u cross v. So to find v, okay, remember v is actually a vector that is actually kind of pointing along the y direction. Okay, so then that means this is the y component, and also it's pointing a little bit up. So then I have the z component. So this v vector has a y component and a z component. If you look at this picture again, some y component and some z component. And on the other hand, this red vector has some x component and also some z component. Okay. So this length here is just dy. And if I want to find this z component, I need to know dz1. So, but just from what we learned before in chapter 1, right? So this dz1 is just given by this partial f partial y dy. Okay, so this dz1, this one. So then my v vector, right, it's just my dy y hat plus dz1 z hat, which is this. And then I just rewrite it here. So similarly, for the u vector, right, so I need to find the x component and the z component. So the x component is just dx. And the z component, this dz2, right, is given by this derivative partial f partial x by dx. Because when you walk along this direction, you are fixing y, but you are just moving along the x-axis. So then similarly, my u vector is written like this. So I have u, I have v, then I can do the cross product. Okay, doing the cross product, write it as a determinant, right? So at the end, I got this one. So this is the same as what we obtained from using the argument of the gradient vector. Okay. So if you don't like or if you don't think that the gradient vector's argument is a bit more difficult to follow, you can try this one. Okay. So let's try some simple example here. I have this curved surface, okay, given by this x to the power of 3 divided by 2 plus y. So this is my curved surface. And then I want to find this surface area over this region R. Okay, what is the region R? The region R, right, is defined right on the xy plane. So it's it's this region in the xy plane. Right, both x and y goes from 0 to 1. So it's a square region in the xy plane. I want to find this part here. So just follow the formula, right? So first of all, this double integral, the limit is easy to do, right? Both x and y go from 0 to 1. Okay. And then I just need to take care of these derivatives here. right? This partial f partial x, right? Just take this one here, partial f partial y, also this one here. So and then plus 1. So that at the end, I just get a very simple double integral, okay, for you to do, and this is a number. Okay. So another example is that I have a hemisphere. Okay, I want to find the surface area of this hemisphere. Okay, so you might remember last time we have already done it using not last time but maybe last week when we talk about the last example in the triple integral, right? When we do the spherical coordinate example. So, but here I'm just doing it again, but using the formula we have just learned. Okay. So here we are actually staying with Cartesian coordinate here. Okay. So I want to find the surface area of this one. Right. The sphere can be written as this g function equals 0. Okay. And then I'm going to consider the hemisphere. So that means I'm going to just consider the z equals 0 or above. Okay. So then that means you could see that what we are going to do. Okay, so of course again is to find the normal vector. So the normal vector this time will point something like this. Right. And this is the integration region that we'll need to take care of. The integration region will be a circle in the xy plane. So now I'm just using the same formula here. Okay, so then taking the gradient should be straightforward. Okay. But here, when we set the integration limit, again, we need to be careful, right? Because I'm considering this spherical region in the xy plane. Okay. So that's why I have these two integration limit here. Okay. Because this can be written as y equals 1 minus x squared, right? This half here. And then the other half over here is y equals minus 1 minus x squared. Okay. So that's why this is the two integration limits. And you have seen it. You have seen it in the last chapter. Okay. But anyway, this is not the easiest way to do it because, as you know, that using spherical coordinate will be the easiest. But here, anyway, we tried in this Cartesian coordinate with the formula we just learned. Okay, you'll find, of course, the result you expect again. Okay. So now, what we are going to do is to not just consider the surface area. Okay. But suppose I have this some function, okay, defined in the 3D space. Okay. So suppose I have again, let me use temperature as a function. Okay. I have some temperature function is this entire 3-dimensional space. Okay. And then of course, that every point in this curved surface, right, you can measure the temperature. Right. So suppose I want to find, suppose this curved surface is some kind of temperature detector that you can detect the temperature at each small element. Okay. And if I want to ask what is the average temperature that your entire detector received. Okay. then what you would do is to actually, right, take the temperature value here, right, multiply by this area, and then you do it over and over again, and then do the entire integral. And then at the end, you may also want to divide the whole thing as the whole surface area. But regardless, okay, if you want to do something like that, you are considering a double integral. Okay, you are not just integrating for this d sigma, but for each d sigma, you are multiplying some value g. Okay, but at the end, okay, so whatever physical meaning it means, okay, all you do is just that you just put the function here, right, and then you integrate over this dx dy. Okay, but this is not the main items that I want to talk about. Okay, the main thing that I want to talk about is actually again the flux. Okay, so that means in this case I'm considering at each surface area element I have some scalar value. But what we really care about, okay, more importantly, is that suppose now I want to put this surface in a vector field. Okay, so now at each element of this surface, I have some particular vector. Okay, so just like what I show here. Okay, so this is my curved surface, and all these arrows, okay, refer to the vector field again, given by this one. Okay. So now, if I want to find the flux, okay, across this surface or through this surface S, then this is the integral that I'm going to do. Okay. So at each element d sigma, I have to consider the vector field at that point. Okay, this F is the vector field at that point, and then I need to take the dot product between this F and this normal vector. Okay, and then multiply that by d sigma, and then do the double integral. Okay, across the entire surface that you care about. Okay. So then this is the flux, right, across the surface or through a surface. So, however, one thing to take note is that when I talk about n, right, so n, of course, as I've said already, is the normal vector for this d sigma, right? But you can always have two choices, right? Whether it's like pointing up like this, or the exact opposite direction, pointing down. So in that direction, actually define the orientations of your surface. So basically define which one is your front, which one is your back. Okay. So and before you do the flux integral, right, it's important for you to make a decision first. Okay, whether you pick this one as your n or the other one, the one that's going down as your n. You need to pick that first. Okay. So after, for example, if I pick this upward as my n direction, then a positive flux would means that the field go up. Okay. But similarly, if you pick your n vector to be going downward, then the field go down will give you positive flux. Okay. So here I give you a simple enough vector field. Okay, so this is, you have seen x hat plus y hat. Okay, so now I have this z hat. Okay, so basically it's still referring to a situation where the vectors are all diverging out, right, from the origin. But as you can see in this picture, okay, they are all diverging out from the origin of the coordinate system. Okay. So now I choose this flat plane as my surface, I call S1. Okay. I want you to find out the flux, okay, towards the z direction, okay, through this surface. Okay. So this surface is easy. Okay, it's just a square, right, a plane, right? So situated at z equals 2, right? And it goes from x minus 1 to x equals 1, and then goes from y equals minus 1 to y equals 1. Okay. That's a square plane. Okay. So if you want to find the flux, right? So what you need to do, right? First of all, pick your normal vector, right? Normal vector, because I say already, okay, it was the z direction, not the negative z. So that's why you pick the n hat to be the z hat. Okay. So, and in this case, the d sigma is also very simple because it's not a tilted plane or it's not a curved surface, right? It's just a plane parallel to the xy plane. So that's why my d sigma is exactly just dx dy. Okay. So now, then I just need to do what is the integrand? The integrand is f dot n, right? F dot n, because n is just z hat. Then you just basically have the z component. Just having this extra plus sign here. Okay, so and then the dx dy limit, the x and y limit, of course, are simple in this case. I can just go from -1 to 1, and then this -1 to 1, and at the end you get the result like this. Okay, I think I would like to stop here for today. Okay, so we have some new concept today, right? So we move on to this vector fields in 3 dimensions. Okay, we looking for flux, right? So, and next time we'll continue with more complex examples and some theorems for this 3 dimensions.係啊，係啊，即係因為呢個係因為我呢個有呢個係呢個係係咯，呢個又係你個 M 嚟嘅，呢個就係 M 喎。呢個 derivative 學過喎，即係嗰個呢個 second derivative 學過，有冇學過？即係呢個符號，即係 partial y、partial x 擺埋一齊。係啦係啦，即係我逢親係咁寫嘅話，係咯，就即係話就一定係咁樣，一定係咁。呢個定義嚟嘅，係啊係啊，呢個第一課提到，係啊係，係啦係啦，即係你可以即係咁樣，即係咁樣睇咪睇得舒服啲。總之你係咯，後邊嗰個先嘅，啊，所以係咯，所以就一定係，就係咁。